Hi all, Dave out in Western Pennsylvania, USA, and I put together a simple PowerPoint overview of some very fundamental experiments that can be done with supercap components. I'm thinking of electrodes, the electrolytic solvents that can be used in supercaps, and this is geared and directed towards undergrads and home researchers that are interested in supercaps and energy storage. This short video will simply focus on power output studies with graphite felt, commercial graphite felt. The graphite felt I obtain from vendors on Amazon. Generally, the resistance with a multimeter measurement is 0.9 ohms per centimeter, which is certainly not copper or aluminum, but it's conductive enough that the flexibility of the graphite and the cost of the graphite, it's worthy of study as an electrode and is used as an electrode in batteries, of course, and supercaps. So here we're going to see how a sample of graphite without any type of modification or perhaps a few coats of aerosol graphite spray on the surface of the felt. That's an interesting study itself. But in any event, a commercial graphite component in series circuit with twin commercial supercapacitors. Next slide. Now, the objective of measurements, varying voltages and effect on step-level power outputs. I'll step back a little bit. And what we're doing is taking a section of commercial graphite felt and treating it with 2 or 3, as I mentioned, coats of aerosol graphitic spray, commercial graphite spray. And I'm interested in knowing whether that can actually provide a little bit of surface area. Now, the graphite spray has a binder, organic binder, but that's what I used here. And 15-minute delays were used after each coat, both sides. I didn't even write the mass down, but you get the picture. My prior videos will outline this approach with the spray. Now, the following data that I'm presenting here, preliminary results as voltages at time 0, and we're going to vary those voltages as I'll show you, and future videos will show the results with modified graphite felt. Electroplating nickel, cobalt, nickel-cobalt alloys. Those are electrode depositions. Now, you don't want to deposit too much of those metals or you lose your flexibility of the graphite felt. So we generally do light nickel plating, 4 volts, for about 1.5 minutes each side, but that'll be a separate video. Now, you can also attempt to oxidize the graphite felt. Permanganate, nitric acid. I use oxone, swimming pool bleach. Oxone, O-X-O-N-E. Very interesting results, leaving it in a 20% solution of oxone, aqueous solution, for a couple of days. Sonication. And as the graphite is modified before use in supercap prototypes, in other words, I want my students to focus on the components, the electrolytic solvent and the electrode, the nature of the electrode. Here it's graphite. And such applied research is really suggested for undergrads and home researchers interested in energy storage. Supercaps. Now, it's very important to have a feel for the components. And then if there is a problem, you can identify, is it the electrode? Is it the solvent you're using, the electrolytic solvent? Maybe it's not electrolytic enough. Some students will progress to graduate school where they'll be using very expensive equipment, but even my students will be using a potentiostat and scanning electron microscope and FTIR. But let's show you what I'm driving at here. Here's the next slide. Experimental design. 2 commercial supercaps, I get them from Amazon. They're rated each at 2.8 volts and 100 farads capacitance each. I placed them in a simple circuit bench scale using alligator clips because I'm not moving the circuit around. The theoretical potential, putting them in series, would therefore be 5.6 volts, right? Double the potential in series, but you cut the capacitance to 50 farads. Now, why am I doing this? Because I want to be able to see how the graphite and in wet studies with an electrolytic solvent, how it holds up at higher potentials than what you find in commercial supercaps with organic solvents like dimethylformamide or carbonates. And they're sold at usually 2.7 to 2.8 volt potentials for safety. And I want to see if we can go to higher potentials. So can we actually see any evidence, collect any evidence that the electrode and the DES electrolyte, deep eutectic solvent electrolyte, can they hold up at 3.7 to 4.8 volts? Realistically, I would think if I can get it to 3.7 to 3.9 volts, well, that's a big jump over 2.8 volts, isn't it? So we're building supercap prototypes eventually with DES electrolyte solutions. Now, how does modification of graphite affect conductivity? Can we boost the conductivity of the graphite? For example, oxone can oxidize the surface of graphite felt and produce alcohol groups, carbonyl groups, oxygenated surface, which can increase interaction with less hydrophobic, let's say, less hydrophobic. And of course, we'll be studying that with scanning electron microscope, looking for subtle changes. Nickel plating, of course, can produce contact points, and that can increase conductivity. So we want to see if the DES electrolytic solutions we're testing remain electrochemically stable. In other words, what's the window? 3.7 to 4.8 volts. Now, what we will do in experiments not shown here, but in prior videos, we can carry out 300 to 500 cycles with an electronic load device. ZB Tech is what I use. And we can compare the capacities for each charge-discharge. And we want to see that ideal ratio of 1:1, which means you're not losing heat. But that's a separate experiment, not done here. The E-load device, ZB Tech Model 10H, that one allows you to do cycles and step levels, which we will do here. These are reliable devices, very inexpensive, and they can be purchased, for example, at Amazon. The last time I checked, we were paying about $115 US each, and the shipping charge. And I think we have about 10 or 11 of them, and they are very good value in my estimation. The software downlink will be in the operator's manual. So, of course, then the software is netted plus. Now, experimental design part 2. A section of graphite with dimensions, sorry about the typo there, of using a caliper 26.5 millimeter width, 52.8 millimeter length, and 3.6 millimeter thickness. That's what I used as a component in this circuit. I forgot to write the mass down, but my other videos can give you an idea of the masses of these dimensions. Stainless steel clips, I got them at Walmart in the craft section, and I pressed them onto the graphite, and then I use alligator clips to attach for these simple preliminary studies. No DES electrolyte solutions were applied in this study, and the graphite component was exposed to the surroundings. In other words, I did not seal it in a plastic bag or a container. I'm just running it so it's exposed to the surroundings. The negative black lead of the load device was attached to one clip and the other clip to the rest of the circuit with the twin supercaps to follow. They're in series, and don't go up to 5.6 volts, because if you don't have parallel resistors in the circuit, you could have voltage imbalance and destroy the supercap or both of them. So we stay well below that 5.6 volts potential. But by putting it in series and having the setup to the E-load device, this ensures the current must discharge, right? It has to go through the graphitic material before reaching the supercaps. And if you don't hook this up the right way, if you put it in parallel, it could be bypassed. So you want to make sure that their graphite is going to be directly in touch with that E-load device, and then the other lead goes to the supercaps. And I'm using alligator clips because I'm not moving this around, so I didn't solder anything. Next slide. Experimental design 3. The system was charged to voltages, charging at potentiostatic constant voltage, and I used 3 voltages. I charged it up to 4.9, 3.8, and 3.7 volts with a current of 750 milliamps and a trickle charge current to a cutoff of 0.15 amp. Then within 10 seconds, I started step levels. And I noted the open voltage right at the start of carrying out step levels. Now the step levels were carried out with the following input values. Steps of 0.1 to 1.0 amp. So we had 10 steps, 10-second intervals with a 0.3 volt cutoff for the circuit. And a run without graphite component was carried out for comparison. That's important. I want to see how much resistance this section of graphite is presenting in the circuit. Here's the first experiment. Experiment number 1. Supercaps alone, no graphite component. So we charged up to 4.9 volts, and then the open circuit right at the start was 4.71 volts. Now take a look at the current values in amps. 10 steps from 100 milliamps right up to 1.0 amp, and the corresponding watts. Now just make a rough idea. You can go back here in the video, but when you get to about a half an amp, you see how the power output is increasing. In the beginning, you have a small current, but as you increase that current, you're starting to get increased power output. So you can see about half of these numbers are 2.0 watts or higher. Now that's with the 2 supercaps without the graphite. Now let's see in the next slide. Experiment number 2, supercaps with the graphite component. So we charged up again, potentiostatic charge, constant voltage, 4.9 volts, and at open it was 4.71 volts when we started the study. There's the 10 steps, and you can see the wattage goes from 0.4 watts, 0.8, 1.2, 1.4, 1.7, 1.8, 1.8, 1.8, 1.6, 1.3. Now, if you compare that to the prior slide, of course, the power output is going to be dropping because of the graphite not being a tremendous conductor. But it does conduct. And the point is, can we boost the conductivity of it through various means that I had mentioned? So compare these numbers. Now let's go to the next slide. Experiment number 3. Here we have the capacitors only now. I took the graphite out and charged up constant current, 4.1 volts, and cut off when trickle charge reached 0.15 amps. And we charged up at, what did I tell you, 750 milliamps. And the open voltage was 3.8 volts. Now this is the capacitors only in the circuit. And we're using a smaller potential, 3.8 volts actually to start. So there's your currents. And then you can see the wattage. So you can see what we get by dropping down where the study starts at 3.8 volts. Experiment 4, supercaps and graphite components. 4.1 volts, and then open was 3.8 at the start, 3.8 volts at the start, and you can see the currents and the wattage output. So as we're dropping voltage, we're getting smaller power output, and you can compare those numbers with the prior slide. And then we go to experiment 5. Supercaps only, but we're going to drop the potential down from charging up at 3.70 volts. It opens at 3.56 volts. There's your currents and there's your wattage output. And that's the supercaps only. Now, when you go to the next slide with the graphite, you can see greatly diminished power output because of the graphite offering resistance. Now, of course, your copper leads, any copper leads you're using, the clips, right? Well, copper is not a superconductor. It's going to offer a little bit of resistance, but the major source of resistance in this circuit would be the addition of the graphite component. So here we started at 3.7 volt charge, and the opened voltage was 3.40 at the start. That's usually in about 10 seconds. And there's your currents, and there's your power output. Greatly diminished. Now, if you go back and compare all these numbers, let's go to the next slide. Conclusions. Each step level was carried out twice with essentially identical values. So, of course, we can do a statistical analysis of it, but we didn't see any major. The results were very reproducible for 2 attempts at each experiment. For comparison of the standard supercaps with the graphite components inserted, the highest voltage, of course, 4.9 volts, showed a 300 or 400 milliamps as a reasonable current draw similarity with the graphite there. So if you're going to work at high voltage, 4.9, then 300 to 400 milliamps. For the 4.1 volt comparison, I would stay below 300 milliamps current draw. I would stay down around 200 milliamps. For the 3.7 runs, I would stay once again below 300 milliamps. Now, of course, not all supercaps have to be kicking out 500 milliamps. You might say, I want an application where I'm going to draw 100 milliamps. But it's up to you to look at the data and determine where you think you would want to stay at a given open voltage. We will next run graphite wet. See, these are dry graphite studies. And wet means we're going to apply selected deep eutectic solvents, and they have to be conductive. Now, we use zinc chloride, acetamide in a 1:4 molar ratio, or choline chloride urea in a 1:4 molar ratio, respectively. They are not conductive. They're very easy to prepare. About an hour in the lab and you'll have them, and they'll be liquids, but they're not conductive. Now, there are conductive DESs, but they're not cheap. And what we found, we were initially using lithium tetrafluoroborate, and which is not cheap, but an industry standard. But we found lithium bromide anhydrous. We dried it in the oven at 100 degrees Celsius for 24 hours. We stay away from lithium iodide because it's hard to keep dry, and lithium iodide is going to be inclined to undergo redox chem, and we just want an electrolyte. So we took lithium bromide, and we found that it dissolved with a little bit of warming, about body temperature, and with good stirring, it'll go in. And once it goes in, when it comes back to 20 degrees Celsius, we have not seen it precipitate in even 3 weeks or more. It stays in solution. So now you have an electrolytic solution to test on the graphite. So these are very simple experiments. Now, future studies. We want to carry out cycles of charge-discharge, maybe 300 cycles. I've already done 300 or 500 in experiments, and they may have to run for 24 hours. And we want to compare the milliamp hours, the capacities for each cycle of charge-discharge, and look for an ideal one-to-one ratio, Coulombic efficiency. And we want to see if the mass of the DES solution remains constant when we put it into a closed plastic sleeve. My other videos will show you that. We heat seal it, and we use these baseball cards, plastic sleeves for sports cards, and we'll also examine the Fourier transform, FTIR, forgive me for the typo, FTIR. What we'll do is squeeze out some of the solution after it's been running and look at the FTIR before and after to see if there are any noticeable changes. We also carry out scanning electron microscopic studies. We're getting in a brand new SEM. It's been ordered, and we'll be looking at 10 to 50,000 magnification, looking for subtle changes or maybe major changes in the graphite materials. Now, I also have graphite yarn, twine, and that's interesting, but that will require some thought in how to study it. So right now we're working with the felt, and we will also attempt to apply slurries of expanded graphite, which I have from Asbury Graphite Company, Asbury Graphite in Pennsylvania. And they gifted us, they were very generous in gifting us various graphite materials they manufacture. And I have expanded worm-like graphite. Now, I'm not going to get into a discussion of expanded graphite and exfoliated graphite. They're basically one and the same. Let me just say that. But it's very worm-like looking with a lot of low density. But I want to make a slurry up in a DES and see if I can apply that to the surface of graphite felt to boost conductivity. Preliminary experiments show this could be the case. Now, if we can bring bench scale supercaps to 3.7 volts with cheap DES solutions with lithium bromide as electrolyte, this would be significant in our opinion. Commercial e-supercaps with organic solvents, as I mentioned, like DMF or alkyl carbonates, are sold at 2.7 to 2.8 voltage windows due to safety reasons, leakage, fire hazards, stability, chemicals, electrochemical stability, and we want to see how these DESs hold up. Now, if you start to see any changes in charge-discharge cycles, if you see any changes in 50 cycles, well, it's not going to work out in a supercap. And if you go 300 to 500 cycles and it's not changing and it's close to a 1-to-1 ratio, well, that's good. It's encouraging. But remember, commercial supercaps can be tested at 500,000 or 1,000,000 cycles of charge-discharge. But for home researchers and undergrads, if you don't see any problems at 300 cycles of charge-discharge, that's encouraging. And that's how you learn. So our prior videos will have my website link, and also be tolerant of my amateur artwork. That's a stress reliever for me, and I enjoy putting up some of the artwork that I do there. in between studies. Thanks for watching. Dave out in Western Pennsylvania, USA. Bye for now.